Let us begin with the fundamental building block of graph theory, the graph. A graph is made up of vertices, also called nodes. We place 5 vertices labeled V1 through V5 in a pentagon arrangement. Each vertex represents an object or entity. On their own, vertices are just isolated points waiting to be connected. Now we add edges. Each edge connects a pair of vertices. E1 joins V1 and V2. E2 joins V2 and V3, and so on. We continue adding edges until 6 connections are in place. These edges represent relationships between the vertices. Formally, we write G equals V, E, where V is the vertex set and E is the edge set. The vertex set V contains all 5 vertices, and the edge set E contains all 6 edges. Together, they completely define the graph. And here is the complete graph, with all its vertices and edges displayed together. The simple structure of vertices and edges is the foundation upon which all of graph theory is built. Let us explore adjacency and neighborhood in graphs. We highlight vertex V2. 2 vertices are adjacent, or neighbors if they are connected by an edge. The edges incident to V2 light up one by one. Each edge leads to a neighbor. V1, V3, V5, and V6. The neighbor set n of V2 equals V1, V3, V5, V6. Now, let us define the degree of a vertex. The degree of a vertex is the number of edges incident to it. We count them: edge 1, edge 2, edge 3, edge 4. The running total climbs to 4. Therefore, the degree of V2 equals 4. This means V2 has 4 neighbors. We clear the count labels. For comparison, deg of V1 is 2, deg of V3 is 2, and deg of V5 is 3. This leads us to the handshake lemma. Imagine a party. Every time 2 people shake hands, each person's handshake count goes up by 1. In graph terms, each edge contributes 1 to the degree of each of its 2 endpoints. So every edge is counted exactly twice when we sum all degrees. The handshake lemma states, the sum of all vertex degrees equals 2 times the number of edges, written as sum of deg of V equals 2 times absolute value of E. Let us verify by double counting. We iterate through every edge. For each edge, we add 2 to a running counter, because each edge touches 2 vertices. Edge by edge. The counter climbs 2, 4, 6, 8, 10, 12, 14. With 7 edges, the total reaches 14, which is exactly 2 times 7. Double counting confirms the lemma. Each edge was counted once for each endpoint, giving us exactly 2 per edge. Now the per vertex breakdown. Deg of V1 is 2, V2 is 4, V3 is 2, V4 is 2, V5 is 3, V6 is 1. The sum is 2 plus 4 plus 2 plus 2 plus 3 plus 1, which equals 14, and 14 equals 2 times 7, confirming the lemma. An important corollary follows directly. The number of vertices with odd degree must always be even. In our graph, V5 has degree 3 and V6 has degree 1. 2 odd degree vertices, an even number. This is no coincidence. To summarize, adjacency defines neighbors, degree counts, incident edges, and the handshake lemma links total degree to edge count. These are the foundational tools for graph analysis. Let us learn about paths. Here is a graph with 6 vertices and several edges connecting them. A path is a sequence of vertices connected by edges. Watch the dot traverse along the path step by step. We write this path as the vertex sequence. This is a simple path. No edge is repeated and no vertex is revisited. A cycle is a path that returns to its starting vertex. Watch V0 to V2 to V4 to V1 and back to V0. The cycle is a closed vertex sequence. The defining property of a cycle. The start and end vertex are the same. Now, connectivity. This graph is connected. Every vertex can reach every other vertex. But watch what happens when we remove 3 critical edges. The graph breaks apart into separate pieces. The graph is now disconnected. The vertices separate into 2 components, component 1 and component 2. Each is a maximal connected subgraph. Try as it might, the red dot cannot find a path from one component to the other. There is no edge to cross. A graph is connected if there exists a path between every pair of vertices. Otherwise, it splits into components. Paths, cycles, and connectivity are essential graph theory concepts. Let us explore how to find paths and detect cycles in a graph. Starting with breadth, first search. We mark vertex v0 as the start. From there, BFS explores layer by layer. Distance 0 is the start itself. The first frontier ring expands outward to reach its direct neighbors. At distance 1, vertices v1 and v4 turn green. At distance 2, the frontier reaches v2, v3, and v5. At distance 3, v6 and v7 are discovered. The BFS tree edges are highlighted in orange. These edges show how each vertex was first discovered. BFS always finds shortest paths from the start vertex. Now we trace the shortest path from v0 to v7. Distance labels on each vertex guide the way. Edge by edge, the shortest path lights up in yellow. A traveling dot moves from source to target, confirming the route has length 3. The shortest path is displayed with its exact length. BFS guarantees no shorter route exists between these 2 vertices. Now we switch to cycle detection using depth-first search. DFS dives deep into the graph before backtracking. The path display shows the current trail of exploration. When DFS at v6 checks its neighbor v2, it finds v2 already in the current path. This back edge reveals a cycle, v2, v3, v7, v6, and back to v2. In contrast, the BFS tree edges form a structure with no cycles at all. A tree is precisely a connected graph without any cycles. Pathfinding and cycle detection are essential tools in graph analysis. Here is K5, the complete graph on 5 vertices. Let us explore subgraphs. We split the display into 3 panels. Each shows a different type of subgraph: general, induced, and spanning. In a general subgraph, we choose a subset of vertices and a subset of edges. Vertex v4 is removed along with its edges. V' is a subset of V. E' is a subset of E. Now, the induced subgraph. We select vertices 0 through 3, highlighted in green, and remove v4. The crucial difference, we keep every edge whose both endpoints remain. The rule is E' equals all edges with both endpoints in V'. Finally, the spanning subgraph. Here we keep all vertices from the original graph. Every vertex flashes green to confirm they are kept. We remove some edges. V' equals V. E' is a subset of E. To summarize, a general subgraph removes vertices and edges. An induced subgraph keeps all internal edges. A spanning subgraph keeps all vertices. Take a moment to compare the 3 types side by side. Understanding subgraphs is essential for analyzing structure and solving problems on parts of a graph. What happens when we strip edges from a connected graph? 6 vertices appear in a hexagon labeled V, 1 through v6. 9 edges connect them. The graph is connected with 6 vertices and 9 edges. We begin removing edges one by one. First, 3 diagonal edges that are not bridges. After each removal, the graph remains connected. 8 edges still connected. 7 edges still connected. 6 edges still connected. Each check mark confirms survival. Now we remove one more. 5 edges remain, which equals 6 minus 1. This is a spanning tree. Every vertex is still reachable using the minimum number of edges. What if we remove one more? The graph splits. Removing any edge from a tree disconnects it. The components drift apart. The graph is broken into separate pieces with no path between them. We restore the spanning tree to examine it. We examine 5 key properties. First, the tree is connected. A path exists between every pair. Second, it has no cycles. Third, the edge count equals vertex count minus 1. Fourth, removing any edge disconnects it. Fifth, there is a unique path between any 2 vertices highlighted in blue. We break the tree into a forest. Removing one edge splits it into 2 trees. A forest is a disjoint union of trees. With 2 components, edges equal 6 minus 2. A forest with k components has v minus k edges. Removal reveals the hidden structure of graphs. Let us explore the subgraph hierarchy. We begin with the largest set, all subgraphs of G. This blue circle contains every possible piece of the original graph. Inside it, we find 2 families. Induced subgraphs keep all internal edges. Spanning subgraphs keep all vertices. Where they overlap, we get G itself. Nested inside spanning subgraphs. Spanning trees use the fewest edges while keeping the graph connected. Consider graph G with 5 vertices and 7 edges. An induced subgraph on vertices 0, 1, and 2 keeps all 3 edges. A spanning subgraph keeps all 5 vertices but drops 2 edges. G itself slides into the overlap. A spanning tree uses only 4 edges, the minimum to stay connected. Each example slides into its proper place within the Venn diagram. Spanning tree fits inside the innermost teal circle, the narrowest subgraph category of all. Now we arrange these types in a nesting chain. Subgraph contains induced and spanning subgraphs, and spanning subgraphs contain spanning trees. A special relationship holds. The intersection of induced and spanning subgraphs is exactly G itself. Both conditions restore the original graph. The Venn diagram returns to center. Here is the key insight of the subgraph hierarchy. Induced plus spanning means keep everything, all vertices and all edges. That gives back the original graph, nothing removed. This nesting structure is the foundation of subgraph theory. Subgraph traps. Can you spot the mistake? Trap 1. This claims to be an induced subgraph on A, C, and D. Is it correct? No, the edge A to D exists in the original but is missing. An induced subgraph must include all internal edges. The correct version includes both edges among A, C, D. An induced subgraph preserves every edge among the chosen vertices. Trap 2. This claims to be a spanning subgraph, but vertex E is missing. A spanning subgraph must include every vertex from the original graph. The correct spanning subgraph has all 5 vertices with a subset of edges. Every vertex must be present for it to be called spanning. Trap 3. Is this a tree? 5 vertices, 5 edges. But a tree needs n-1, so 4. 1 extra edge creates a cycle. Removing 1 edge breaks the cycle. Now we have 4 edges and 5 vertices, satisfying the tree condition. The graph stays connected and acyclic, a valid tree. Trap 4. Is this a subgraph of G? Edge A to C is not in the original. A subgraph can only use edges from G. Removing the fake edge gives the correct subgraph. Every edge must exist in the original graph. The vertex set is a subset of V, and the edge set is a subset of E. To summarize, induced subgraphs need all internal edges. Spanning subgraphs need all vertices. Trees need n-1 edges with no cycles. Subgraphs only use existing edges. Keep these rules in mind. Let us study graph homomorphism. Here is graph G with 4 vertices and 5 edges drawn on the left side. And here is graph H with 3 vertices and 3 edges drawn on the right. A homomorphism maps each vertex of G to a vertex of H. Vertex A maps to 1, B to 2, C to 3, D to 1. Notice both A and D map to the same vertex. Edge AB maps to edge 1, 2. Formally F maps vertices preserving edges. Now, let us consider a stronger concept, isomorphism. Here is graph G, drawn as a square with 1 diagonal, and graph H, same structure, different layout. The mapping is bijective, P to W, Q to X, R to Y, S to Z. Each vertex in G maps to exactly one unique vertex in H. Corresponding edges flash green in both graphs. The mapping preserves every edge. An isomorphism is a bijective edge-preserving mapping. When one exists, G is isomorphic to H. This brings us to the concept of a graph property. Is this graph connected? Yes, it is. Rearranging vertices does not change connectivity. A graph property is invariant under isomorphism. These mappings are central to graph theory. Are these the same graph? This is the central question of graph isomorphism. Two graphs, G on the left and H on the right, each with 5 vertices and 6 edges. Both share the degree sequence 3, 3, 2, 2, 2. Same degrees, but are they truly the same graph? We construct a vertex mapping F. Each pair of corresponding vertices is highlighted in a unique color with arrows connecting them across the two graphs. We verify that corresponding edges match. Each edge in G has a counterpart in H, flashing green in unison. All 6 pairs match perfectly. The decisive moment. We rearrange graph H to match the layout of G. Vertices slide into identical positions and edges reconnect identically. G is isomorphic to H. But what about these two new graphs? Both have 6 vertices and 7 edges. Let us investigate further. Both graphs share the degree sequence 3, 3, 2, 2, 2, 2. Once again, the degrees match. Is this enough to conclude they are isomorphic? Not so fast. We check triangle count. Graph G on the left contains 2 triangles highlighted in red. Graph H on the right has only 1 triangle. This is a structural difference. These graphs are not isomorphic. Triangle count is a graph invariant. Isomorphic graphs must always have the same number of triangles. The takeaway is clear. Same degree sequence is necessary, but not sufficient for isomorphism. You must check deeper structural invariance to distinguish graphs. Not all graph mappings are created equal. Let us explore the morphism spectrum, step by step. We begin with the funnel. At the top, the broadest category, homomorphisms, which preserve edges. Adding injectivity gives monomorphisms. Adding surjectivity gives epimorphisms. Combining both yields the isomorphism, the most restrictive class. A concrete homomorphism. G has 4 vertices, H has 3. Vertices B and D both map to the same target. The red rings highlight this collapse. The map is not injective. 2 vertices merge. Edges are preserved, but vertex identity is lost. Next, a monomorphism. Every vertex of G maps to a unique vertex of H, but H has an unused vertex in red. The map is injective, not surjective. Now an epimorphism. Every vertex of H is reached, but 2 vertices of G share an image. Vertices C and E both land on vertex 2. The map is surjective, not injective. Finally, an isomorphism. Both G and H have 4 vertices and 5 edges. Every vertex maps on Tn, every edge to an edge. Golden rings confirm a perfect bijective match. Same graph, different layout. Now watch the morphism space filter down. All homomorphisms appear as gray dots. Removing non-injective maps leaves monomorphisms in teal. Further filtering removes non-surjective maps, and the surviving golden dots are isomorphisms. The key formula: isomorphism equals homomorphism intersected with bijection. An isomorphism is a homomorphism that is also a perfect Onotune correspondence. This hierarchy is central to graph comparison and classification. Isomorphism pitfalls: 3 common mistakes to avoid. Pitfall 1. Same degree sequence. 2 graphs, G1 and G2, each with 6 vertices and 6 edges. Both share degree sequence 3, 3, 2, 2, 1, 1. Does this mean isomorphic? No. In G1 degree, 3 vertices are adjacent. In G2, they are not. Different structure. Same degree sequence, but not isomorphic. G1 has 1 triangle, while G2 has 0. Different triangle counts confirm these are distinct. Pitfall 2. Different looking, but actually isomorphic. Here are 2 graphs that appear quite different at first glance. We relabel vertices with matching colors to reveal the correspondence between the 2 structures. Watch as we rearrange the second graph to match the first. Vertices slide into new positions and edges reconnect identically. These are isomorphic. Layout does not matter. Only structure determines isomorphism. Pitfall 3. Complex graph invariance. The Peterson graph has 10 vertices and 15 edges. Verifying its structure requires checking many invariants. Key invariants to check: vertex count, degree sequence, triangle count, and cycle structure. In summary, same degree sequence does not imply isomorphic. Different layout does not mean non-isomorphic. Always verify structural invariance carefully. In degree sequence is necessary but not sufficient. If 2 graphs are isomorphic, then all structural invariants must match. But matching invariants alone does not prove isomorphism. Never rely on just one invariant. Use multiple checks to confirm or deny isomorphism. How do graph theory concepts relate to each other? Let us build a map of their connections. At the center sits the graph, the most fundamental concept. From it, we branch into 5 color-coded categories of related ideas. Below nodes cover foundations, graph, adjacency, and degree. Green represents traversal, paths, cycles, connectivity. Teal covers trees and forests. Now we connect the foundation concepts. Adjacency is defined by the edges of a graph. Degree counts how many edges meet at a vertex. And adjacency determines the degree, counting all incident edges. These 3 relationships form the foundation chain. Every other concept builds upon these core definitions. Next come traversal concepts. A path walks through edges. A cycle is a closed walk, returning to its start, with no repeated internal vertices. Connectivity asks whether every vertex is reachable from any other. Subgraph concepts appear. Taking a subset of vertices and edges gives a subgraph. Keeping all internal edges makes it induced. Covering all vertices makes it spanning. Connectivity leads to trees, and trees produce spanning trees. A forest is an acyclic graph, a disjoint union of trees. Finally, morphism concepts. A property describes a graph. Properties preserved under mappings define isomorphism. And isomorphism is a bijection that preserves edges in both directions, a special case of homomorphism, completing the upper region of our map. Here is the complete graph theory concept map. Every node connects to its dependencies through labeled edges. This structure reveals how foundational ideas unlock understanding of advanced concepts.